There I was, minding my own business, sitting on my tuffet, eating my curds and whey. Say, what are curds and whey, anyhow?
I had to make a lot of noise to get a day named after me.
I'm not washed up at all. Come inside. I'll tell you all the dirt.
I came, I saw, I changed the calendar. When you're roaming inside, make a date with me.
If you've ever had the chance to see clothes spin around in a dry cleaning machine, you know that there's some kind of liquid in there. So why do they call it dry cleaning if it really isn't dry at all? Well, it's called dry because the process doesn't use water. You see, some clothes can shrink or lose their color when washed in water. However, many garments can be cleaned safely with chemicals called solvents, which dissolve stains. Dry cleaners put the solvents and clothes into a machine that looks like a normal washing machine. The clothes are put through a few clean and spin cycles. After that, they're dried. Finally, they're ironed in the big pressing machine. Now, your favorite shirt is as good as new without using a drop of water. Let's say a leaky pen just left its signature right in your shirt pocket. What can you do? Call in a spotter. No, he doesn't put spots in, he takes them out. The spotter analyzes the stain to figure out which chemicals will remove it. Then he cleans the spot with the right chemicals. Nylon stockings can stretch from small, crumpled bundles to fit almost any leg. Where do you suppose this amazingly stretchy yet strong fiber comes from? Well, nylon was the first synthetic fiber ever made. Synthetic means that the material is man-made using chemicals rather than being a natural fiber like cotton or wool. Nylon was first made back in 1938 when a group of scientists were studying the structure of giant molecules. One day they mixed some chemicals containing carbon, hydrogen, and nitrogen, and they came up with a material that stretched like warm taffy candy. Even more surprising, when it cooled, it got stretchier still, and it was amazingly strong. After working 8 long years, they perfected the textile fiber that we call nylon. Making nylon is a lot more complicated than processing a natural fiber such as lamb's wool. Here's how it's done. Water, air, and chemicals from coal, petroleum, or natural gas are combined to form 2 different kinds of molecules. These then form into one larger molecule, which is called nylon salt. Then the nylon salt molecules are heated in a giant pressure cooker. They're heated until they hook together into a long chain of nylon salt molecules called a polymer. The polymer becomes a thick liquid when heated. Then the polymer is forced through tiny holes in order to form thin fibers. The fibers harden as they cool, and then they're wound together to form a yarn. After this yarn is stretched to 3 or 4 times its length, it becomes strong and elastic, and we have nylon. But one word of caution, this is not a project for your home chemistry set, so don't try to make nylons. It's a lot easier to buy them at the store. Why is it that when you spill ink on a tablecloth, it leaves a bad stain, but when you spill the same ink on your skin, you can wash it right off. The reason is that when you wash, you're really rubbing off a layer of skin and getting to a clean layer underneath. You see, your outer skin has no blood vessels or nerves. Instead, it's composed of 30 layers of dead skin. As we wash off layers on top, other cells replace them from below. So, where does the soap come in? Well, the top layer of skin is covered with an oily substance that mixes with dirt. When you wash, soap forms lots of little bubbles. The surface tension of these bubbles attracts the dirt and removes it. Soap also breaks and dissolves those oily layers. Add a little water to rinse it all away, and you've got clean hands. Soap is a relatively new idea in human history. The ancient Greeks and Romans, for example, depended on massages and sweat baths to clean their skin. And in the Middle Ages, people weren't too keen on cleaning of any sort. In the court of Catherine de' Medici, Queen of France, in the 1500s, there were no bathroom facilities at all. Rooms got so filthy that the court moved 90 times in 6 years so they could clean up dirty rooms. Even the stately Palace of Versailles in France, which was built in the 1700s, had no place to take a bath. It did originally have one bathtub, but it was moved outside and turned into a fountain because no one was using it. So how did they clean themselves? Well, they used a lot of perfume. No kidding, several times a day. "30 days has September, April, June, and November. But have you ever wondered where the names of the months come from? First of all, the Egyptians called them moonths because their calendar was based on the moon. The Romans changed the calendar a number of times. They had a 10-month calendar. Then around 700 BC, they added January and February as the 11th and 12th months. However, by 46 BC, the Roman calendar was out of whack again, and all the holidays were happening in the wrong seasons. Emperor Julius Caesar decided to fix things by adding 85 days to that year, instituting the leap year, and changing New Year's Day to January 1st. However, many of the names of the months refer back to the calendar before Caesar changed it. Pick a month to find out where its name comes from. January, the first month of the year, is named after the Roman god Janus, the god of beginnings, endings, and, believe it or not, doorways. That's why Janus has 2 faces, to keep watch in both directions. February comes from the Latin word Februa, the festival of cleansing and purification. When February was the last month of the Roman calendar, it was the time for purifying the temples and cities to prepare for the new year in March, sort of a Roman spring cleaning. March gets its name from Mars, the Roman god of war. It was the first month of the year all over the ancient world, probably because it was the beginning of spring, a time of planting and renewed growth after the long winter. We don't really know much about this one, but some people think that April comes from the Latin word aperire, meaning to open. Maybe that's because so many flowers bloom in April. Here's another name of uncertain origin. May might be named after the Roman earth goddess Maia, or it could be a month in honor of the Maiores, or elders. June was named after Juno, the queen of all Roman goddesses, or it could also have been a month named in honor of Juniores, the Latin word for youth. Julius Caesar, who reformed the calendar in 46 BC, decided he deserved to have a month named in honor of himself. July is for Julius. Emperor Augustus, the next emperor after Caesar, fiddled a little bit with the calendar too and gave himself a month of his own. Of course, his month is August. September means 7th month. Remember, we're counting from the old Roman calendar when March was the first month of the year. October means 8th month, counting from the Roman calendar which had March as the first month of the year. November means 9th month. Of course, nowadays November is the 11th month, but in Roman times it was the 9th. December takes its name from the Latin root deca, meaning 10. Remember, the Romans celebrated New Year's in March, so to them, December was the 10th month. Originally, the Egyptians named the 7 days of the week after 5 planets, the sun and the moon. The Romans used the Egyptian system. We get our names for the days of the week from the Anglo-Saxons, the Germanic people who came to populate England. They named the days after their own gods, which were roughly the same as the Roman gods. However, in most languages, you can still find the planets in the names of the days. Pick a day and find out. Sunday was named after the day of the sun, or Sonnendag. In German, it's Sonntag. But the Italian, French, and Spanish use a word that comes from a phrase meaning Day of our Lord, because in the Bible, God rested on the 7th day. The day of the moon was Monendag, or Monday. In German, it's Montag, but in French, it's Lundi. In Spanish, it's Lunes, and in Italian, Lunedì. These words go back to the Roman name for the moon. This day was named after Mars in the Roman week, so in Spanish it's Martes, French Mardi, and Italian Martedì. The Anglo-Saxons dedicated it to Tiu, their god of war, so they called it Tuesdag. Wednesday had been named for Mercury in the Roman week, but the Anglo-Saxons named it after their chief god, Woden. That's where we get Wednesday. The Italians, French, and Spanish go back to the Roman. In Italian, it's Mercoledì, French, Mercredi, and Spanish, Miércoles. The Roman day of Jupiter became the day of the Anglo-Saxon thunder god, Thor. Thursday is Thor's Day. In French, it's Jeudi, Italian, Giovedì, and Spanish, Jueves, all using the Roman Jupiter as their base. The Romans named Friday after Venus, and in French it's Vendredi, Italian, Venerdì, and Spanish, Viernes. The Anglo-Saxons named it after Frigg, the wife of their god Woden, so we call it Friday. Saturday, the Roman day of Saturn, was translated into Saturnsdag. In French, it's Samedi, Italian, Sabato, and Spanish, Sabado. A woman sprints on an Olympic track in Seoul, Korea, and seconds later, an audience in New York City cheers her on. How do those images get transmitted to TV sets on the other side of the world? They get there through communication satellites. These satellites orbit the Earth, receiving and passing along television and other communication signals. Here's how they work. A TV signal is sent or transmitted from a station in the country where the event is happening. The signal is beamed up to a satellite which strengthens or amplifies the signal and sends it to another station. Since television signals can only travel in a straight line and the Earth is round, often several satellites must be used to send the signal from one location to another. That's how we can receive television pictures from any part of the world almost instantly. What keeps a television satellite amplifying and transmitting year after year? There are no plugs, no wires or batteries. Why doesn't it just run out of energy and stop? Because it's powered by one of the strongest and longest-lasting energy sources in the universe, the sun. Satellites are covered with solar cells. These cells collect energy from the sun in order to produce power for all the functions the satellite performs. Today, scientists are trying to find other ways to use the sun's energy because it's cheap, efficient, and can't be used up like the Earth's non-renewable energy sources such as gas and oil. We already use solar energy to heat houses, run pocket calculators, even to fuel experimental cars. Although all the bugs haven't been worked out yet, the idea of solar energy is so promising that it wouldn't be surprising if one day most of our machines, appliances, and electronic gadgets were powered by the sun. Here's a riddle. What do you get when you cross a radio with a telescope? Why, a radio telescope, of course. Regular optical telescopes see light, so they can only show us things within the visible spectrum. But there are many more objects and events that are beyond the realm of visible light, and they give out other forms of energy. That's where radio telescopes come in. They gather energy signals given off by distant stars, and scientists use these signals to figure out information about these stars. This radiant energy is collected on Earth by large dish-shaped receiving stations, where computers determine what kind of energy it is, where it comes from, and analyze what it means. Radio telescopes have even told us about spiraling nebula, exploding stars, and black holes. Scientists can look at the information from radio telescopes either in the form of a chart or as a computer-illustrated picture. Have you ever wondered what keeps a satellite spinning through the darkness of space without falling out of the sky? Well, it has to do with a famous idea called Newton's first law of motion. This law says that an object will continue in a straight line unless something stops it. So, according to Newton, if you were shooting marbles, each marble would move forever in a straight line until it hit another marble, or a wall, or the friction of the floor slowed it down. But what's going to stop a satellite? Why doesn't it just go off forever? Well, the Earth's gravity pulls down on the satellite. So why doesn't it fall back to Earth? The answer is that the satellite has just enough velocity, meaning it's going just fast enough that its forward movement equals the rate it falls due to gravity. As the satellite moves forward, gravity pulls it back into orbit, so it just keeps going around in a circle. So will satellites stay in orbit forever? The answer is no, because thinking about Newton's first law of motion again, something is going to slow it down. That something is friction. You see, the motion of the satellite through the atmosphere causes friction, and that friction will eventually slow the satellite, just as it would slow a marble rolling across the floor. When the satellite slows enough, it can't keep its orbit, and gravity will pull it back to Earth. But the reason we don't worry about dodging falling satellites is the same reason they fell in the first place: friction from the atmosphere. As they fall, the friction produces heat so great that the satellite usually burns up before it reaches the Earth. A boomerang may look like a harmless toy. It's just a curved piece of hard wood that whizzes through the air in a graceful arc. But did you know that it's actually one of the oldest and most peculiar weapons ever invented? A boomerang is curved at an angle of between 90 and 120 degrees. One side is flat and the other is rounded, and each arm of the boomerang twists slightly in the opposite direction. The pressure of the air on the bulge of the rounded side, together with the twist put on it when it's thrown, makes the boomerang circle back and return to the person who threw it. The native Australians, known as Aborigines, can do incredibly skillful things with boomerangs. They can toss them so that they travel straight for 30 yards, make a circle 50 yards across, and return to the thrower. Although we associate boomerangs mostly with these Australian Aborigines, people have used boomerangs as weapons in many other places, including India, Africa, and the United States. Did you think that all boomerangs return to the thrower? If so, you're wrong. There are two kinds of boomerangs, and only one comes back. The non-return boomerang is nearly straight and heavier than the returning kind. It's used as a weapon, and in the hands of an expert it can really be deadly. And the return boomerang? The native people of Australia sometimes use it for killing birds to eat, but mostly they think of it as a toy. But be careful with boomerangs anyway. They can still hurt someone. When an earthquake topples buildings and cracks streets, how do scientists measure its power? They use sensitive instruments called seismographs, which detect movement in the Earth's crust. You see, there are cracks in the upper layer of the Earth's surface. These cracks are called faults. The rocks on each side of a fault constantly rub up against each other as they slowly shift position. The force of that rubbing movement can produce earthquakes. So how does a seismograph measure an earthquake? One type of seismograph is made so that a firmly fixed chart lies parallel to the ground, like a piece of paper. Above it is a rod with a weight on it, and attached to the weight is a pen which just touches the chart. When there's an earthquake, the chart moves along with the movement of the earth, but the suspended weight doesn't move. The pen draws lines on the chart as it moves, giving us a visual record of an earthquake. An earthquake's strongest point is always the place on the Earth's surface where the shifting actually takes place. This point is called the epicenter. A seismograph can pinpoint the epicenter by measuring two kinds of seismic waves called P and S waves. These waves travel at different speeds through the Earth. Calculations based on the time of arrival of each of these waves at the seismology station tell scientists where the earthquake was centered. And there are different kinds of seismographs to record different kinds of earthquakes. In some quakes, the earth moves horizontally from side to side, and in others it moves vertically or up and down. Today, scientists are very interested in trying to predict earthquakes. By looking at seismographic records of past quakes and by studying day-to-day records of activity at fault lines, they hope to discover patterns that will help them predict quakes. If they can tell when a quake is coming, they can warn people to take steps to protect themselves. The word thermometer comes from the words thermo, meaning heat, and meter, to measure. So a thermometer measures heat. Mercury is the perfect material for a thermometer because heat makes mercury expand and rise. Mercury will always rise to the same point when the same amount of heat is applied. To make a thermometer, a small amount of mercury is put into a tube with a bulb at the bottom. The upper part of the tube, the part without mercury, is either left as a vacuum or filled with gas. Then a numbered scale is added to tell us the level of mercury. When you use a thermometer, the heat that your body is producing makes the mercury in the thermometer rise. If your body produces just 2 degrees more heat than normal, the mercury will go up 2 degrees from 98.6 to 100.6. Many modern thermometers don't use mercury anymore, but they still register the rise and fall of body heat. And a note of caution: mercury and its vapors are highly toxic, so don't experiment with it unless you have supervision. There are two main measurement scales used to describe temperature. The Fahrenheit scale is used mostly in the United States, while the Celsius scale, also called centigrade, is preferred in countries that use the metric system, such as countries in Europe. On the Fahrenheit scale, water freezes at 32 degrees, whereas it freezes at 0 degrees on the Celsius scale. Water boils at 212 degrees Fahrenheit and 100 degrees Celsius. There's an easy way to convert Fahrenheit to Celsius so you can read both types of thermometers. Start with the Fahrenheit reading, subtract 32, and multiply the answer by 5/9, 5/9. You'll find that 75 degrees Fahrenheit equals about 24 degrees Celsius. To go from Celsius to Fahrenheit, multiply the original number by 9/5, then add 32. So if you hear that it's 15 degrees Celsius in London and 59 degrees Fahrenheit in New York, you'll know that both places are the same temperature. Have you ever heard a weather forecaster predict rain because of an incoming low pressure system? Air pressure is related to the movement of hot and cold, moist and dry air in the atmosphere. We measure air pressure with an instrument called a barometer. The most accurate kind of barometer is a Mercury Barometer, which uses the rise and fall of mercury to reflect the changing pressure of the atmosphere. In a Mercury Barometer, atmospheric pressure forces mercury into a vacuum tube until the weight of the mercury is the same as the outside air pressure. We can read the air pressure by looking at the numbered scale measuring the height of the mercury. At sea level, the average height of a column of mercury is 29.92 inches. If air pressure drops, the mercury goes down and we can predict windy, stormy weather approaching. When the mercury rises, we have fair weather. Mercury is used in barometers because it's the Earth's heaviest liquid and its movement is very small, so a very small tube can be used. If we used water instead of mercury, we'd need a tube 30 feet high.
A weather forecaster isn't the only one who can use a barometer to predict the weather. Click on the barometer and you can too.
A barometric reading of 29 inches or less indicates low pressure. Warm air is rising, being replaced by cold air from below. Looks like storm weather. Around 30 inches of pressure is the average reading on a barometer. The weather here could go either way, giving way to high or low air pressure. When the barometer reads around 31 inches or more, it means high pressure. Odds are the weather here will remain fair for a while. Have you ever been told that you're letting out the cold when you leave the refrigerator door open? How do you suppose the cold gets in there in the first place? Well, chemical substances called refrigerants, such as freon and ammonia, are circulated through tubes in your refrigerator. When these refrigerants change from gas vapors into liquid, heat is released. Here's how it works. First, a pump compresses the vapor like a bicycle pump compresses air. This heats up the vapor, which is then sent to the condenser. The condenser turns the vapors into a very cold liquid. This produces heat, which is released outside the refrigerator through the coils of the condenser. The cold liquid now flows to the evaporator, which is the compartment that cools the contents of the refrigerator. The heat in this space is slowly absorbed, causing the liquid to evaporate back into a vapor. It returns to the compressor and condenser, where the heat once again escapes to the outside, and the cycle is repeated over and over.